Okay, when we ended the notes for the last part, or the first part of chapter 4, we started talking about equations and how to balance them. Because again, remember, we balance equations to satisfy the law of conservation of mass, which says matter cannot be created or destroyed. This comes right from your book. Okay, I just put it in here to review how to balance equations. One of the important things to remember is you can only use coefficients. You can only use numbers in the front. Do not change the subscripts. And in this page, I will also put a couple YouTube videos that'll help you if you haven't balanced equations for a while or you didn't really understand much of it. So you'll just have to go through it a couple of times and hopefully you'll get it. Okay, so here's our equation. We've got iron and oxygen. We get Fe3O4. Okay, so you can see I only have one iron here and I have 3 here. So I'm going to put a 3 there. And I have 4 oxygen here and I only have 2. So by putting a 2 here, now if you look, 3 iron, 3 iron. 2 times 2 is 4 oxygen, 4 oxygen. So by putting a 3 there and a 2 there, I balanced my equation. Okay, on this one's pretty simple, right? Because there's a 2 here, so I'm going to have to put a 2 here. And then I'm going to have to put a 2 here. Okay? I don't know if I did that. Yeah, I did. Okay? Oh, I should have made this subscript. Anyway, SR, I have 2. I have 2. I have 2 oxygen, and now I have 2 oxygen. So those were pretty simple. But if you get a complicated one like this one, this is called a combustion reaction, and they're kind of the hardest ones to balance, but they really aren't if you follow a simple rule. Carbon first, hydrogen second, save oxygen for last. If you do your carbon, you do your hydrogen, and you find out you have an odd number here, and you can only do even number here, double the first one. Okay, so like here, if I put an 8 here for carbon, and I put an 18 here, or a 9, excuse me, a 9 to get the 18 here, well, I'm going to 9 and 8 is 17. I have an odd number and I have to have an even number. So I'm going to put a 2 here. So I put a 2 here and I get 16. So I put 16 here. And 2 times 18 is 36. So I'm going to have an 18 here. Well, if you add those together, 8 times 2 is 16. Oh, I doubled that, right. Sorry, 16 times 2 is 32. Plus another 18 here, 32 and 18, 50. I'd have to put a 25 here. And I know that sounds complicated, but really, I did my carbon, and then I did my hydrogen, and I saved my oxygens for last. So now if you look, 2 times 8 is 16. I got 16 carbon. 2 times 18 is 36. 18 times 2, 36. Now I have 16 times 2 is 32 oxygen here and 18 here, because remember, it's this half versus that half. 32 plus 18 is 50. Put a 25 here. 25 times 2 is 50. So they can be like this, or they can be simple ones like this. But again, it's just putting numbers in front to balance your equations. Okay. Remember, from a balanced equation, you can also do what they call stoichiometry, where you can figure out if you start with so much reactant, how much product you can produce. And this is something you use a lot in industry, because if you have to produce, ammonia, which they use a lot in farming and fertilizers and so on, then you need to know how much stuff to start with so you can produce the amount of product you need, for whatever amount you sell. So that's stoichiometry, and it's checking out, calculating the mass of your products from the mass of your reactants. How much stuff, it's kind of like a recipe. Like if you're going to make cookies, if you're going to make, 2 dozen cookies, you probably need 1 bag of chocolate chips. If you're going to make 4 dozen, you better buy 2 bags of chocolate chips. Otherwise, your chocolate chip cookies are going to be kind of cheap. You're only going to have a few chocolate chips in them. So it's important that you know the right amount of your reactants so you can produce your products. Okay, those are stoichiometry. And again, you use the mole ratios from the coefficients. That's why you have to have a balanced equation to do these. Okay. I'm just going to review a little bit. I'm not going to, this is, something we spent quite a bit of time on and if you took Chem 115 or 121. So I'm just going to talk about it a little bit, but I'm not going to spend a lot of time on it because we'll do more with the equations and like the conversions of moles and grams and stuff. Okay. Here's an example. How many grams of water produced from 34 grams of hydrogen? Okay. Well, first thing you need is a balanced equation. If you don't have a balanced equation, you cannot do these problems, okay? So what I'm going to do is I'm going to start with 34 grams of hydrogen. I'm going to switch it to moles because I need to compare moles of one substance to moles of another. So in order to do that, I'm just going to take 34 grams of hydrogen times 1 mole on top and its mass on the bottom. By its mass, I mean its formula mass, what it weighs. Okay? So the first thing I'm going to do is I'm going to take my 34 grams of hydrogen. I'm going to go 1 mole is 2 grams. And where I got the 2 from, this is H2. Hydrogen is 1, but there's 2 of them. That's where I get the 2 grams. This is 2 grams of hydrogen. Then I'm going to do a mole ratio. This is where I need my balanced equation. Okay, so I put the moles that I start with on the bottom, and I'm trying to find water, so I'm going to put that on top. These numbers come right from my balanced equation. Okay, if I was doing oxygen, then I would only use 1. But there's 2 to 2, so I put that in there. And then my last step, because I want to know grams of water, I put 1 mole of water on the bottom and 18 grams, and that's the mass of water. So I just take 34. I'm not going to multiply by 2 and divide by 2, you guys. I'm just going to go 34 times 18, and I'm going to divide by 2. And I get 306 grams of water. So when I start out with 34 grams of hydrogen, I can produce 306 grams of water. If I need to produce more than that, I better add more hydrogen. If I need to produce less, and some people think, well, just throw a whole bunch in there. Well, that's not cost effective. You know, you need to get close to the amount that the exact amount you need so you don't waste money. You know, that's important in industry. They don't like to waste money. Okay? All right. So when you have a chemical reaction, you're going to have a change in energy. Usually it's heat. Okay? When you're talking about energy, you're talking about the capacity to do work. Okay? And you're going to have, work is the act of moving an object over distance. And you're thinking like, wait a minute. Heat? Yes, heat is energy. Okay? It's moving air. Okay? So it's not like what we think of, like when we think of work, we think like pushing something or picking up something or whatever. But heat does that. Okay? So chemical reactions transfer heat energy. They absorb it from the surroundings or they release it. Okay? Those are the 2 times. A chemical reaction, if it absorbs energy, it actually gets cooler. Okay, the system gains energy, so the surrounding area gets cooler. Because when we take the temperature, we're doing the surrounding area. We're not actually doing the reaction. Okay, if it gets hotter, if you take its temperature and it gets warmer, then that's a different type too. It's releasing energy to the environment. So the 2 types, or the where you get the energy from is you have to add energy if you want a chemical reaction because you're going to break bonds. Okay, you're going to break bonds and then you're going to form new bonds. Well, if it takes less energy to break the bonds and form them, then you're going to, gain energy. That's going to be what they call an endothermic reaction. If it's just the opposite, where it takes more energy, then you're going to release energy, and that's an exothermic. Okay, the difference between them, you'll see them down here. Really, the big way you can tell is if it gets colder, the surrounding area gets cooler, the energy's been absorbed, that's an endothermic reaction. If it gets hotter, energy has been released to the environment, that's an exothermic. Okay, and they call that enthalpy. Enthalpy is change in H. That's the change in the heat, basically. That's what enthalpy is, pretty much your heat. Okay, so if your heat, your exothermic reaction, if heat is released, then your change in energy is going to be less than 0. It's going to be a negative number. Okay, that's an exothermic. And if your change in heat, your change in enthalpy is a positive number, greater than 1, that's going to be an endothermic reaction. And again, if you measure it by temperature, this one gets hotter, this one gets colder. Okay, so whenever you have a chemical reaction, you're going to have a change in energy. If it gets hotter, it's an exothermic. If it gets colder, it's endothermic. Okay. Here's one way they use to measure changes in enthalpy. It's called a calorimeter. They do this when on your food. If you look at your food labels, you have the calories. Those are actually kilocalories. This is what they did. They burned it and they measured how much it changed the energy. Okay, so they use these reaction. They're called calorimeters, and they measure calories. Okay. All right. So when you have food energy, you're combusting of food in the presence of oxygen. That's what your body would do if you eat something, you add oxygen to it. That's how you break things down. The energy that's released, you're actually going to burn it. Okay, and combustion means to burn something. So all the energy released by combustion then is absorbed by water in your bodies. That's why we're 70% water. And then we use that energy for whatever we need. So we need exothermic reactions. We have some endothermic reactions, like sweating is an example of an endothermic reaction. Because when the water evaporates from your system, it takes heat with it. That's why you cool down. Okay? So the calories absorbed by the water that's given off when you burn the food, is the calories, okay? And so they can determine that with those calorimeters. They burn the food, and then the heat is put in the water, and then you measure the difference there, and that'll tell you how many calories you have, okay? Here's showing carbohydrates, fats, proteins. Later on, we're going to talk about biochemistry, and we'll talk about those biomolecules. Carbohydrates, proteins, fats are what they call biomolecules, okay? And we'll talk more about those later, I promise. Okay, so when you're talking about chemical reactions, okay, you have a series of biochemical reactions that lead to producing some sort of product. It happens in your body. Thank God we don't have to think about it, right? But it's a biochemical pathway. And again, we'll talk more about these later. But one, it's funny, most people, when you say metabolism, they think that's the process of breaking down your food. That is metabolism, but metabolism is all the reactions that occur in your body, not just breaking down your food. There's actually two of them. There's anabolic. Anabolic means making stuff. So like when you take amino acids and build proteins, that's anabolism. And if you're having a hard time, remember, think of anabolic steroids. You know, some people take those to build muscle, okay? Catabolic means to break things down. Okay, and in our body, that's what we're doing all the time. We're building things and we're breaking things down and building things. Like I eat a hamburger, my body breaks it down into amino acids. Then I take those amino acids and I put them in and I build muscle tissue. Okay, so anabolic means to build, catabolic means to break down. And those are your two types. And all of them together make up your metabolism. So again, catabolic is converting large molecules into small molecules, breaking it down. Anabolic is building large molecules from small molecules. But both of those together are your metabolism. So your metabolism isn't just you breaking down your food. That's actually a catabolic pathway. Okay? So your body has all of those things. And again, we'll talk more about those when we do biochemistry. Okay? Catabolic pathways release energy. Anabolic pathways absorb energy. Okay? So again, they need, when you break stuff down, you get energy from it. Excuse me. When you want to build stuff, you need to absorb energy. Okay? And again, all of the energy required to build from that, we make in our cells from breaking down glucose, and it's called ATP. Again, we'll talk about that later. But anyway, that's the energy that occurs in your body. Okay? So, we're done. We're done with chapter 4. So again, keep working on your assignments. If you got questions, let me know. But for right now, we're done with chapter 4.